up to but not including position 3. Okay, so it's sorted from 0 to n, but round bracketed n. Okay, so it's sorted from here to here. Clearly, it's not sorted after that. Okay, and x is 1. I want to insert it in here, so I'll end up writing the 1. The 4 will move over and overwrite the 2. I've lost the 2. Is that clear? Is the meaning clear what I wanted to do? Yeah? Is that a yes or a no? That's a yes. Okay. All right, so here's my code, which is partly scraped off. So I've got int I equal to 0. Then I start searching for, I skip over all the AIs that are smaller than x because I have to put x in sorted order. And then I'm going to, after this while loop is over, I found the position I at which I want to write. That may already have something in there, so I copy that over into a temporary. Okay. I'm trying to confuse you by speaking fast. There's a bug in the code, so please look for the bug. Okay, I'm making it sound like it's absolutely right. So I want to write in position I copy it over into a temporary. I put x into that location, and then everything else I have to push over to the right. And here is my while loop to do that. Clearly, that's right. And I think that's the end of the code. Okay? Yeah. Anyone see a bug? Yeah. Oh, very good. We're incrementing I without checking to see if we've hit the end of the right. Exactly. Very good. So, so what's your name? Ankush. Ankur. So we could ask Ankur, and Ankur told us the answer. But oh, okay. The whole box. I thought Stanley was the one who thought of this. You'll make a lousy first slip to dive across. Okay. A lousy first slip to a left-handed person. That way. Okay. So we're going to ask Ankur, but we're going to ask Dafny. Okay, that's the tool we're learning about. That's not Dafny. That's the researcher who more or less did Dafny, but he's got beautiful hair. I said I have to find this picture of him. If you see some of his YouTube videos, it's amazing. It actually gets more amazing than this. He looks neat compared to some of the pictures. But Rustan Leno, he used to be at Microsoft, now been poached to Amazon. Used to work on this. So if you go to Dafny's web page, that's there. You won't find too much mention of Rustan, but he's involved in the development of this code. So there's a web interface for Dafny. So if you want to try it out, you can try it out. It's a lot of fun. You will learn a little bit of the syntax, which you'll learn by the end of this lecture. You'll have got enough of it. You can be dangerous with Dafny. But you can also download it. And so there's some options over there. And you can run it on your own laptop. Okay. So Dafny cannot reason directly about C code. We have to translate it into Dafny. So it's a language, but it's also, the name is also given to the verifier. Okay, Dafny. So we're going to write in Dafny. So we have to take our code, which I wrote over here, and I have to translate it into Dafny. So as I said, you'll get a sense of how Dafny syntax looks like. Okay, it's not so difficult. So this was void insert, and then int star, etc., etc. So this is what it looks like in Dafny. It's quite readable. It's method insert. Okay, and you don't have these explicit pointers. You say it's an array of integers. Okay, Dafny has a data type called nat because we want n to be the length. We don't want it to be negative, so we don't have to do defensive coding. We just say it's a natural number, and it just won't let you run it with a negative number. Okay, so we say there's actually a natural number, but the thing you want to put inside could be a negative number. So that's an int. Okay. Assignments are different. Just like with Alloy, single equals means equality. No, actually it doesn't. Never mind. Colon equals is assignment. Okay. And then while loop is similar, except you don't have to put the round brackets, and you don't have a plus plus operator. Okay. So like that, you can kind of figure it out. Okay. It's quite simple. I mean, this is an example where it's a very simple match, but it's actually not so bad. Okay. And I hope you agree it's quite readable, right? All right. So let's ask Dafny about this. So let me see if I can move this guy over. So I've got a local version of it. So I'm not using the web interface. So there it is. So that's all the code. I've got the code up. Oops. So the code up here. And Dafny, the IDE, is checking at compile time if it can prove things about this, right? And it's saying that it's highlighting that while loop, and it's got a message over there, which is also interesting and worth seeing. So let me see if I can pull it up here. It's saying at this line, sorry, let me show you, that's a warning. Here, this is the line, the red ones are the interesting ones. The red one says it cannot prove termination, right? And, when does it terminate? We don't know, right? I mean, maybe this is never true. It'll just keep going on and on and on until you get out of bounds, right? So it's in its own way, it's telling us the problem. So it's found the bug. It says I can't prove termination, and it tried to prove termination, and in fact, it even tried to figure out, if something is terminating, the way it proves it is it tries to show that something decreases to 0. And it says, well, you're checking if AI is less than or equal to X. So I'm guessing maybe that you're trying to reduce the gap between AI and X. As I sound, I can use that to wake you up. I can sound thunderous. So it's trying to guess that might be the thing that's going down, the gap between AI and X. Okay, of course that's not what's going on. That's not what's going on. It's not decreasing to 0, so that's clearly not right. So that was its guess, but it says it can't prove termination. Okay, so we have to add the extra constraint. Okay, so let me just show that to you. So while I is less than n, okay, and that part of the syntax is similar. Okay, so now it's saying index is out of range. Okay, is it? Is index out of range? So let me tell you a little bit about how Dafny is reporting. Okay, I'm not telling you about how Dafny is working, but how Dafny is reporting. When Dafny is sure that something is right, she will remain silent. When she is not sure that things are right, she will say, I'm not sure, but I think there's a problem over here. Okay? So when you see red stuff, it means maybe something is wrong. It doesn't mean something is wrong. So is this a maybe, or is there something wrong here? So maybe there's something wrong. What is n? How is that related to the length of the array? Oh, that happens बाद में, ना? That happens inside the loop. Yeah, but that's inside the loop. I mean, you know how the AND condition works, right? I first check the first condition. It's only if it's true, then I look at AI, right? So, but the problem is it doesn't know what n is. As C programmers, we say, oh, there's an array, and I promise you that the n is the length of the array, trust me. And no one would possibly call it with the wrong n, will they, right? Of course, that happens. So Dafny is finicky. So Dafny is actually right here saying, look, I don't know what n is. I see that you're going up to n, but you didn't tell me that n had anything to do with the length of the array. Okay? So I think Stanley mentioned that you should be aware of Tony Hoare. Okay? And so this is very much in that spirit. I'm going to write a precondition here. I'm saying to Dafny that, look, this function, this method, when you call it, it requires certain conditions, right? In particular, it requires that n is less than array.length. And unfortunately, there's a way of saying that, right? Should I say less than or equal to? Less than or equal to? But I want to insert. There better be a gap. N is how much, I mean, the array is used from 0 up to n minus 1. That part is used. It better be the case that n is less than, because I plan to use slot number n, slot number n, right? Yeah, array is sorted up to n minus 1. I plan to use slot number n. It better be the case that n is less than the length, because later on I will want to write to slot number I, and that I could be as much as n. Okay? So you see that that's sort of done it. Now I haven't got red marks, I've only got green marks. Okay, so this is like a teacher who writes in red when you get it wrong and green when it says, you could do better. Okay, so what is it being finicky about? Okay, it's saying, you know, you could have given me this hint that n minus I is decreasing. Okay, forget it, figure it out yourself. Okay, but you could also add that hint. All right, but then it's still got some red marks down here, right? It's saying assignment may update an element that you didn't tell me that you were going to update. So here again, I have to tell Dafny, okay, and this method requires this, and by the way, it's going to make a modification. It's going to modify A. Okay. By the way, this semicolon is not needed, but it's not wrong to put it in there. Okay. I'm warning it that it modifies it. Okay. It's still not happy about this. And this is one of those cases where Dafny is actually not as accurate as it could be. The code is actually right. Okay, that's not an out of bounds exception. And that's not a situation where it can be out of bounds. We know that, right? We've said that n is less than a dot length. We know that the maximum this I can get to is n. And so this would be a perfectly legal index. Okay, but Dafny is unable to prove that. And loops give Dafny a lot of grief. Okay, so we're going to help Dafny along. Yeah. No. So the model for ints and nats is very robust. There in maths you cannot overflow, so in Dafny you cannot overflow. Okay. In reality, when you run it, it'll overflow, but the proof assumes it's true maths. Okay, and that doesn't overflow. But there's a good question. Okay, so in general, when we write loops, in addition to writing all the stuff that we want to happen, we have to help Dafny along by telling it in each iteration of the loop what conditions are true. What conditions are going to be true when you come back to the top of the loop. Okay, that's called a loop invariant. So this is actually, it's a condition that has to be true before the loop starts, before the first execution. So the first time you check the condition, here's a condition that must be true. And interestingly, this is also a condition that must be true at the end of the last iteration when you're about to quit. So this is not a condition that includes the breaking out case. Okay, it's conditions that are true for all iterations of that loop, including at the beginning of all iterations of the loop, including in the beginning of the last iteration when you're actually getting out. Right? The last one where you decide, oh, I don't have to go into the loop, I get out. Okay, so you have to write an invariant here that says that I is between 0 and n. Okay, and you can write maths-like syntax. Right? 0 is less than or equal to I, which is less than or equal to n. Okay, and then the error goes away. This was our first example of where Dafny panicked and actually didn't need to panic. So Dafny was not going to let you run that code with that error in there. So you had to assure her that no, I is within this range. Is this okay? The second one, it's able to prove that it decreases. You're not using I after all anywhere, so it says, yeah, sure, that's done. Okay. So is this code correct? Well, it does something. We didn't ask Dafny to prove anything about what it does. It does something. It doesn't break any array bounds. It does something. I have no idea what you wanted me to do. You gave me that example in the PowerPoint, but you didn't tell me, Dafny, what to do. So yeah, it's fine. We have to add extra conditions to say, well, what did we want it to do? So far, so good? Any doubts on this so far? Yeah? Okay. This is our warm-up problem. We'll get more interesting. Okay. All right, so this is just a recap. Daphne found the bug. We had to change that. Just as well, we looked at it over there. Those were these decreases are the extra hints that I left in green over there. Okay, that's what it looks like. Put that hint in there, put the invariant in there, put the requires, put the modifies, and then you're good to go. Okay, but as I just hinted, there's more, right? This is what the marketing people tell you. Oh, there's more to this offer, you know. And the more to this offer is we have to say that it keeps the array sorted. Okay, we didn't say that. Okay. So let's see. What I'm going to do is, I'm sorry, this is a little bit out of bounds, but hopefully you'll be able to read it. Okay. So what I'm going to write here is a function, not a method. Okay. So a method is something that you can actually execute. A function, just like the maths function, okay, is something that you will actually use to prove other things. So here I want a function that talks about sortedness, but I won't ever actually run it. So it's like a mathematical comment, if you will, a mathematically precise comment, okay, that I'm creating over here. So here's a function sorted. It takes an array of integers and a natural number n, and I want this function to basically, so it's a function that returns a bool, okay. Later on, you'll see there's a notation which I can just call it a predicate, and I don't have to say that it returns a bool. So a function that returns a bool is a predicate, okay. But here's a function that returns a boolean. It's going to tell me if the array is sorted or not, right? And all you need to do to say if something is sorted, since this is only saying it's sorted from up to, but not including n, okay? So the array itself could be longer, but I want to say the first n elements are sorted from 0 up to n minus 1 are sorted, okay? So all you have to do is you have to say ai is less than or equal to ai plus 1 for all the i's in that range, okay? What I will actually say is the stronger version of it. I will say for all I and for all j, where I is less than j, ai is less than or equal to aj. It's like a strong inductive hypothesis when you do induction, right? So that's what I'll do. And the purpose here is really to show you the notation for that. So they say for all ij, okay, the way to read this is for all ij, double colon just means for all ij, wait, catch your breath. There's an implies over there, which is written in Dafny as equals greater than, okay? So for all I and j, if 0 is less than or equal to I, which is less than j, which is less than n, then ai is less than or equal to aj, okay? For all I and j, if I and j have this condition, then ai is less than or equal to aj, okay? And so that's a statement that is either true or false about the array. The function is returning this boolean, okay? It's saying if this condition is true, then it's sorted. If it's not true, it's not sorted, okay? And once again, I need some requires condition here because otherwise n will be out of bounds, right? I and j will be out of bounds, right? Because I'm going up to but not including n, but I haven't said what n is. So I need a similar condition here. Here, what should the condition on n be? Here I could get away with up to and including the length. Because I'm just saying, is an array sorted up to length n? Well, n just has to be up to length, up to or equal to length. And I also need to assure it that I'm only reading a. In a function, if you're using an array, you need an extra assurance that you're only reading the array, okay? And then what I can do is in my method, my insert, I can require as an extra condition that it's sorted up to but not including n. And analogous to a requires, after the function is done, I'm promising, I'm putting an ensures condition. I'm ensuring that the array is sorted up to and including, up to but not including n plus 1. So I require that the array was sorted up to but not including n, and I'm saying that when I write this code, I promise you, Daphne, that this code, the array will be sorted up to but not including n plus 1. Okay? So that would at least give me something meaningful to aim for the rest of the code. Okay? By the way, do I need any other condition? In order to do what I told you in English that the code was supposed to do I need to say anything more to Daphne about what this code is supposed to do? You're not eligible for chocolate. So, just so you know that. But let others try. If you heard him, he said something about elements. The last element should be? Well, I have to say that x somehow got added in there. And it would have been the expense of some element, right? Maybe the last element. Actually, for this function to work, we don't know whether it's going to be the last one, but the way it's implemented, it is the last one. Okay? But what about all the others? Yeah, what if my modification was just override everything with just x? Then x is in there, but I completely destroyed your original array. I would meet the condition that it's sorted, because sorted means less than or equal to. If I just wrote x's in every place, it would be sorted and it would have x, but it would also be a disastrous function, right? So I'd have to say that all the elements that were there beforehand are also still there, but there's also an x. Okay? So there's some syntax we'll see that when we look at the code. Okay? There's that extra condition that we need to say that we're actually preserving all the old stuff. Okay? Yeah. The question is there an order to requires and ensures? Well, so there's a following order in the sense that when it checks it checks that all calls to this function provably satisfy all the requires conditions, and it checks that the body of this function satisfies the ensures. In terms of the order in which you write them, there are some strange ordering issues, but I'm not familiar enough of an expert to tell you exactly what those are. I suspect those are more unintended programming errors within Dafny's backend code. Okay? I mean, the way I interpret it is that this is a set of requires conditions and no particular order. There's a set of ensures conditions. Kyunji? Yeah? I think that's how it's supposed to be. Yeah? Okay, so let's go to the code and look at that. So this one's lousy. I mean, lousy in the sense that it does what it's supposed to do, but we didn't say what it's supposed to do really. So this is a little better. So I've got, wait, what happened? What happened to my sorted function? Oh, maybe I seem to have ordered things a little bit differently, or maybe I have already gone ahead. Okay. Oh, A2 was where I was supposed to end up after talking about A1. So I've edited A1 to make it look like A2. Okay. All right, here's my sorted function. Okay. Here's my insert. Here my extra requires. Here's my ensures. This is my ensures that is saying that I don't mess up the stuff inside it. Okay. The syntax says that basically, if I look at the slice of the array, the sequence of the array up to but not including n plus 1, and I make a multiset of that because there could be duplicates, right? Then that is the multiset of the old array up to n. So you can call the old value of something, right? Plus x. You can't quite see it. There's a plus x over there. Okay. So that sequence plus x. Okay. So I add x in there. Okay. So that's that condition. Okay. So I say to Dafny, hey, prove this. That assuming it was sorted, prove that it maintains the sorted order. So it inserts it in the right place. Okay. So it goes here and it says I can't prove this. Okay. And it says I can't prove one of the conditions, one of the post conditions, one of the ensures conditions that you have. And it turns out the one that this one's complaining about is that it's sorted. So it says, fine, you gave me something that was sorted. I can't be sure that what I leave you with is also sorted. Okay. So you're all programmers. You know what the code, is trying to do. You've seen the C version of it, but the Dafny version of it is just as understandable. I hand wave to say that this works. You tell me, which case is it? Bug? Or is there just one of those cases where Dafny is unable to prove? Five minutes. You don't get the job unless you clear this interview question. Debugging. So I said it half jokingly, you don't get the job, but you know, right, that most of the job is going to look like this. Somebody else wrote the code, and somebody's gone, right? So, are you going to change the code? It works today. You're going to change the code. Yeah. 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 But n is remaining the same, so the gap between n and I is decreasing. That's what that's saying. Okay. So, it seems like there's no problem. Would you bet your life on that? Or would you bet a chocolate on it? I can promise to give you a chocolate if you're right, or I can keep it back. What do you lose? There's no problem? You can, but I think this one has already done the insert before this while loop. This is just doing the copy over, right? Now, if you were really doing this in C, of course, you would use this library function to do the copy over, right? You wouldn't write your own. You wouldn't dare to write your own. I hope you wouldn't dare to write your own loop to do that, right? But this is Dafny, and we want to see if this is correct. And I just want to give you a flavor of what a good use case of this is. I mean, I suppose your life depended on this, or your chocolate depended on this, which in this case you have earned, right? Ow, sorry. Why is it pointing out an error? Oh, it's saying I can't prove one of your post conditions. I can't prove that this thing keeps the array sorted. But there's no bug. If I give it more hints, it'll prove it. It'll finish the proof that it's correct. Okay, so she was right. She said it looks correct. But I wanted to give you a flavor that, I mean, this is probably, how many of the 80 of us in this room, we could have written at least 15 different versions of this code, right? And maybe we're all a little bit uncomfortable with the way this code is written. I mean, I wouldn't have done it that way. I would have put the I over there. I would have done something. I wouldn't have begun the loop with the I equals I plus 1. It just looks wrong. It seems weird, right? Right. So your gut feeling is no, right? But it turns out it's actually correct. I mean, you can work it out on paper, or you could have Dafny prove it, right? That this is actually correct. But I wanted to just indicate to you as an example that this is not so easy to see, even though it's 4 lines of code inside the while loop, right? I haven't given a loop invariant, right? That's the hint. So I need another invariant over here. I need to tell Dafny what it is that I'm doing. I haven't given any invariants, right? But the same piece of code in the previous file didn't protest because I didn't tell it about sortedness. It's able to prove that it terminates without any further hints. It's only I can scroll up to where it says what the post condition is, pointing to the sortedness, and it's also pointing to the multi-set condition. Both those is unable to prove. Yeah. No, while I is equal to n is the normal semantics. It just won't go into the. Okay. Well, so in the remember the first while loop was trying to find the insertion point. Okay, that insertion point could have been n, right? Because it could have found that the whole array is sorted, and this guy goes at the end of that array. In which case, we really don't want to do anything else, and this will quit. This loop will skip over. But we want Dafny to prove that that is also a valid case, and it should handle that case. Ullas, did you have a question also? Yeah. Well, you need invariants, for broadly speaking, for 2 things. One, to prove termination. Okay. In this case, the loop is simple enough that the loop is simple enough. I start somewhere, and I is less than n, and I keeps increasing. Surely, even if I was, what are the cases? I starts off bigger than n or equal to n, then I won't go into the loop. It starts off below n, in which case it'll increment and the loop will stop. Dafny is perfectly able to prove that this loop terminates without any further hints. The previous condition, before we had added the extra stuff, was ai less than or equal to x. Dafny is like, I don't know. Is that ever going to be true? I can't prove termination. So there I needed some extra stuff, and I needed to give it this hint. Okay. So that's one reason you need invariance. The second reason you need invariance is, and this is typical of the case where you have a whole bunch of stuff going on, variables are changing. Dafny needs to know what are the things that are remaining constant, what are the conditions, what are the relations that are remaining constant, so it can use that as sort of little lemmas to finish proving what it is that it really wants to do. It has insufficient clues at this point about what's going on inside this code. Okay? So this was A3, it's got bad. So you have to write more invariants, okay? And it's much easier to read invariants than write them. So let me just show them to you, okay? It looks scary enough as it is, right? Okay, but just make sure, okay. So this is my extra ensures. Here is my first loop. It turns out I needed an invariant on that in order to prove some facts about what was true later on. What is it that I wanted to say about the first loop? That it was going to skip over all the stuff that was less than or equal to x. That's what that loop did. It skipped over all the stuff that was less than or equal to x. Okay, so I can put this on the next line so that it's readable. So it's saying for all j's that are smaller than I, aj is less than or equal to x. This loop is going for different values of I. All I'm saying is, Dafny, please remember that the condition here is I less than n and ai less than or equal to x. Please remember that all the j's that you have seen so far that are less than I, there also this condition was true. Okay, and then carry that fact forward for later proof, later part of the proof. Okay, how did I know that that was the invariant it needed? Experience, gray hairs, 4 late nights. That was mainly for the second code that I'm going to show you, not for this one. Okay. There's a lovely quote about experience. Experience is a comb that life gives you after you've lost all your hair. Okay, then there was all this stuff, and then look at all the invariants that I need to prove, that I need to state over here. Okay, I can share this code with you if you're interested, but you knock out any one of the invariants, and try and prove it, and Dafny will protest that some part of the proof breaks. Okay. So each one of those was needed, whatever those are. Okay, all of those are invariants. You can kind of see what it is. It's saying that position I was where I had left x. So I promise you, I'm changing stuff, but I'm not changing that. AI is where I left x. I'm at position I. This is now some. I've changed the name of the variable to j for this thing, and I'm saying invariant is that it's sorted up to and including j plus 1, up to but not including j plus 1. Okay. A whole bunch of other stuff that I need to do, and then it's able to prove that this code is actually correct. Okay, so you've seen one example of this. This is for a very, very simple piece of code. Okay, maybe badly written. Okay, let's look at something a little bit more sophisticated. Okay? And I think both pieces of code make the point that I really want you to take away from here. So far, any questions? Yeah. Can the invariants go out of sync with the... Well, of course, but then Dafny won't be able to prove it. You can write anything you want in the invariant, but the whole point is of the invariant is to give Dafny a clue as to what your code is doing. You can write anything you like. So it's the Goldilocks principle. It has Goldilocks story, right? About the soup being either too hot or too cold or just right, right? One of the things I've seen is I think I've written something that's stronger than what eventually worked, and Dafny wasn't able to prove with that. Okay, so I haven't been able to get a great sense of what is right. So there's a lot of this is trial and error, and that's coming to the last point of my talk would be on that point. Okay? There's a little bit of magic, a little bit of jadoo as to what works. Okay, yeah. Okay, very good question. So this is repeated for the benefit of everyone. So he said, is there any need for strong induction? Because don't we have to worry about efficiency? Weak induction just checks I with I plus 1. Why are we doing for all I for all j? So one very, very, very important thing to remember about Dafny is that all the maths that we write over here, is only checked at compile time, not at runtime. Okay, so this is a compile time obligation. It's not actually live code. Okay, the live code is exactly what I showed you on the first slide, apart from the bugs which we fixed, right? Right. So we can afford to give, the earlier question about, well, what if we give stronger hints? Generally, of course, it helps. That's why that one works. And so generally, the strong induction kind of thing seems to work better. Okay, and my second example also brings that point out. Yeah. Yes, it also supports object-oriented programming. It's very powerful that way, and it supports functional. Yeah. What if you write buggy invariants? Sure. Yeah, you can prove anything you like. If you've written buggy code and it matches the buggy invariant, it says, yeah, it does what you want to. And then someone tells you that's not what we wanted to do. Right? So, yeah. Yeah. Yes. Although I haven't explored that part much, there is some support for that kind of stuff. Deepak, have you explored any of that stuff on the heap and things like that? There is that. So we've already seen things like out of bounds. But yes, there is a model of the heap, and you can reason about stuff on the heap. You can check it up. I don't know specifically about memory leaks. I'm not sure. Have you explored that, Deepak? No, but syntactically, does Dafny support that? Anyway, you can check it. I know there is some stuff. I know you can do things like new, and you can put stuff on the heap. And I believe I don't think there's a delete, so there's obviously some sort of garbage collection going on, so that you keep track of references and things. But I don't know how powerful it is. Okay, so here is the more sophisticated example that I wanted to do, and that's min heaps. Okay, so that's a data structure, right? I should mention at this point, so I said, oh, I'll give them a simple algorithm. Okay, so I thought I'd do that greedy job scheduling, and what I found was that I could write the code, of course, trivially in Dafny, but then you basically have to write out in lemma form almost the whole proof of that exchange argument that proves that the solution is optimal. And I'm like, well, I'm not going to put CLRS into Dafny syntax, right? So that's not going to help. So I picked a min heap. I picked a data structure example. So everyone remember what a min heap is? The array representation of it. Yeah, which of these is a min heap? Just to see if you're awake. First one is for sure. Yeah. I could use a board, or they could use their board metal. I did bring a pen. And there is a pen here. I did bring a pen. Anyway, but you remember it enough? Okay, so just a reminder, that's the root. Those are its two children. Then these are the two children of this guy, and that one's the only child of the other one, right? So you just check the condition that the parent is less than, hey, I've got parents too. Parent is less than or equal to the two children. Okay? That's the condition that I want. Okay? All right. So here's my Dafny function. So now, in the min heap, I'm only doing the insert. Then there's the extract min, which is another long story. Okay, but I'll just do the insert into the thing. So there's my method. You can see it. Method insert. I've got an array representation of the heap. I want to insert n into an array that is already I have an array that already has n elements in it, so it's already filled from 0 to n minus 1. I want to insert x. So very similar to the previous one, except now the array actually represents a heap rather than a sorted array. Okay, so there's a requires that goes in there that I had to put over there because otherwise it was going to be too big. Okay, so it requires some condition on n. It requires that from a up to but not including position n is a min heap. I'll tell you what that function is in a minute. And this is obviously going to modify a just like the previous one, and it's going to ensure that it is a min heap up to but not including n plus 1. Okay. And here's what you do. So m, if you remember how you insert into a heap, you insert it at the end, and then you swizzle up until the heap condition is maintained. M is the only position where the heap property might break. Okay, the heap property is that you have to be greater than or equal to your parent. Okay, everybody has a unique parent except the root. M is the only place where that local condition might be violated. So M is n and A of M is equal to x. That's where you insert it. And then while M is not the root, because root is at position 0, okay, so while M is greater than 0, find the parent helper function. I'll show that to you in a minute. Okay, and if the parent is larger than the kid, then nice cute syntax to swap. Okay, no temps, right? This tuple becomes this tuple. So read this tuple and stick it into this tuple. Khatam, right? And then, of course, make M the place, make P the place where the modification happens. So M now becomes P. Okay? If it's not clear, go back and check your notes, but that's basically the right code. Okay? So this part has no bugs. So now all I have to tell you is what the definition of min heap is and what the definition of parent is. Okay? So here is, I'm using the alternate notion of predicate. So that's just a function that returns a Boolean, special case. So when is something a min heap? Up to the first n positions, well, it requires this condition on n. It only reads A, and it's saying every AI has to be greater than or equal to its parent. Okay, that's the way I'm going to write it. So I'm picking I deliberately so that it's larger than 0. So I is in the range 1 to up to but not including n. For all the i's in that range, A of parent is less than or equal to A of I. Okay? I'm going to call this the local heap property. I'm checking locally at every position if A of I is greater than or equal to A of parent of I. Okay? And I'm saying that something is a min heap if this condition is true at all the positions that you care about. You care only about the first n positions. I'm checking at the first n positions except 0. Obviously, it's not at 0. There's no parent. Okay. And the method parent. Okay. Is it a function or is it a method? It's a function method. Okay. And the reason it's a function method is it's a function because I wish to do maths about it and I wish to reason about it. But it's such a simple thing, and I actually wanted to go into my live code because I want to use it in my code to call. So in some cases, it allows you to do that. You could make, otherwise you can make a method and say the method does exactly the same thing as the function, but it's kind of a bore. You just say it's a function method, and it says, okay, I'll treat both aspects of it. Okay? So it requires I to be greater than 0. You cannot have parent of 0. Okay? And this is just the formula that you have. Okay? Fine? You can check the formula, that's correct. Okay. So I promise you that's correct, I promise you that's correct, I promise you that's correct. So we're done. Except the invariants. I mean, we are done. Dafny is not done. Right? When you give this to Dafny, she goes crazy. So that's the code that I gave. Okay. She goes crazy in a nice way, in the sense that she only complains about one thing. She says, I can't prove that this is a min heap. By the way, I also need that other condition about multi-set, which I've, in this thing I've dropped. Okay, but I want to make sure that it remains all the old stuff plus the X that I added. So it says a post condition doesn't hold, and that seems simple. And I'm very glad I started preparing for this talk last week, because then I had a few nights to get it right. Okay, I had already at that point given up on the job scheduling. I have like 7 versions of that job scheduling that I failed to complete. And it turns out that fundamentally this realization came to me after 2 nights of whacking away at this, is that this local condition of being a min heap is too weak, and I really need a more powerful notion of what it means to be a min heap. It needs a stronger definition of min heap, which at first glance seems to mean that then you're requiring to prove more stuff, but it's just like strong induction. Now that you have this more powerful inductive hypothesis, I can go and prove more powerful things down the road. Okay, so you need a stronger definition of what it means to be a min heap. Okay, so all that remains the same. Saying for all I and j, and the stuff inside the semicolon, the curly brackets is just a hint because Dafny was giving me a green line saying please put this hint in, so I put it. Prove this statement by induction on I for all I and j. If I is in the range where it can have a parent, and j is in the ancestors of I. You see how it's more powerful? It's not just the parent of I. If j is in the whole set, it looks like, but it actually turns out to be a sequence. If j is in the sequence of its ancestors, then aj is less than or equal to ai. My old condition was for every I, a of parent of I is less than or equal to ai. Now I'm saying for every I and all the j's that are ancestors of I, aj is less than or equal to. So you have taken the local condition and pushed it all the way to the root. Okay, that's what I mean. I required something more powerful to be true. Okay, and the first time I realized it worked, I was saying, Dafny, couldn't you prove that yourself? You know, it's so nice to have a tool with a human name, like you can shout at it, right? So you know, couldn't you have figured out that transitive closure, right? Let's just prove that, right? But it wasn't able to do it, so it needed that definition, and then this is the definition of ancestors. It's just a parent relation on steroids, right? So if I is equal to 0, then this I'm returning now another data type. This is a sequence of natural numbers. You can define sequences, you can define sets. I think I could have made this work with sets. No, I couldn't have made it work with sets because you could have duplicates. Think about it. If I is 0, that has no ancestors. Otherwise, it's the parent of I, that singleton, plus the ancestors of the parent of I. Inductive definition. Okay? I think I could have made this work with sets also, but I use sequences. It's okay. All right. And so I plugged that in, then I wrote a whole bunch of other invariants about this, and I thought, that'll do it. And that was one more night because I realized I needed one more thing. I needed to prove some fact about ancestors, and I wrote that as an ensures condition on the ancestors. I couldn't somehow fit this into the rest. This is where it becomes a little bit of black magic. And this is the condition I needed, and I'm still not sure why I needed to say this explicitly. It says that ensure that for all j, or all the j's in the ancestors, j is smaller than I. The index of all your ancestors is smaller than you. You're going that way in the array. Okay? I needed to say that. And I can't say the simpler version, the local version of that in the parent function, saying that the parent is always smaller than the kid. The index of the parent is always smaller than the kid. Parent is smaller than kid sounds weird. Right? Again, I had to use this sort of stronger version that says for all the ancestor indices are smaller than this guy. Okay? So that plus a whole bunch of invariants that look like this, just to gaze at it in some conditions about ancestors, and an additional assert. Asserts in Dafny are not runtime checks, they're compile time checks. In this case, I had an invariant is something you write about all the variables, or potentially all the variables that are external to the loop. If you declare variables inside the loop, Dafny typically wants to know about those as well, if those are important to the functioning of the code. So here there is the very important variable p, which is the parent. So I had to say something about parents. Okay? So that assert condition is about that. Okay? So I had to say that as an assert statement. Okay? So p is one of the ancestors. Okay? Okay. So let me get to the summary of what this was about. Okay? So it's pretty expressive. It is, a lot of cute notation, etc. You can do some amazing stuff. So I have a strong feeling you can teach all of discrete maths through the undergraduate course through this, right? So all relations and all that stuff you can prove, and you can prove. You can do a limit. I mean, the set model is limited because you can only do finite sets, but still you can do some very interesting stuff with it. And it's very curious about the things that it doesn't work on. And Deepak knows much more about that stuff than I do. Dafny is sound but not complete. That just means, in our terms, right? When Dafny says it's right, right? But when Dafny puts a little squiggle, it may still be right. It's just Dafny wasn't able to prove it. Okay, and that by itself is not that amazing. After all, I can write a sound but not complete method, right? You give me a code, I'll just say no, that's not good. Sound. If I tell you it's correct, it's correct. When did I tell you it was correct? Right? So I can write something that's sound, right? But obviously Dafny is much better than that, right? So there is an extreme case of that, and so the interesting case is what it can prove, and it can prove non-trivial things. But to prove non-trivial things, you need non-trivial hints. Okay, and so today, what I don't want you to do is walk away from this talk and say, I don't care about that stuff. I mean, look at the effort the poor guy had to go through to prove 3 lines of code, right? Why should I care, right? And I'll give you a reason to care. Okay, and this is the reason to care. Not so long ago, it was non-trivial to write even the code that I've showed you, right? Non-trivial in human lifetimes thing, even last century, right? Middle of last century, that stuff was bloody hard to write. You have to write actually in zeros and ones on punch cards and all that horrible stuff, right? And look where we've come with IDEs and things like that. As you type, they tell you something, and this thing is proving stuff as you go along. Just a second. So, if I had to bet, I would bet that there will be easier and easier ways to pull out the invariants from the minds of the programmers. There will be more intuitive ways of doing this. It wouldn't be quite so hard. Go ahead. Don't be so harsh on us, yaar. Come, we use more powerful tools, but we're more productive with them. Right? I mean, we can write stuff. We can write stuff like PowerPoint and Dafny and all this kind of stuff, right? No one would have been crazy to write that with machine language, right? So what I'm saying is we're able to do more productive stuff, right? And as I said, I would analogously bet that we will be able to incorporate these kinds of tools more easily. Today, if you really, if your life depended on it kind of thing, I want you to see that there's this tool, and this tool has become hugely powerful over the last few years. Right? I mean, this and a whole bunch of other tools. So they're increasingly coming to the cusp of the way, assembly programmers. Oh my God, they could write an assembly, right? But there's still these gurus, right? So we're, I think, roughly around that place. You've got to be that good, and you've got to know the ins and outs of it and things like that, right? But then something like a compiler will come, that you can write high-level stuff, and it'll compile down to assembly. Then you don't have to think at that nuts and bolts level. It'll come up with it'll suggest invariants for you. Here's an idea if you want to work on this, right? Remember how I explained what the first code was supposed to do to you humans? I gave you an example, right? Now, can I do that? Can I tell Dafny, well, on this example, I wanted to do this. Now, you use that to figure out some invariants, and I'll tell you if those are the right invariants. I can read maths. I can't write it so well, but I can kind of read it. I mean, that stuff, all that stuff I can read. So it's supposed to do this. On this kind of an input, it's supposed to do this. That's much easier. We don't have the tool to go from there to then search for invariants, but I imagine we will get there. Okay? So I think I have 1 minute for questions. Yeah. The question was, can it detect when invariants contradict with code? Well, in the sense, yes, again, it will just show that it can't prove that invariant. That invariant, it says I can't show that. It'll either show, it'll give you one or both of these messages. It can't show that it holds that entry, or it can't show that each iteration maintains that invariant.